So the idea is that these requirements, like I said, have emerged because of the recent emergence of modern collaborative architecture such as GRID and peer-to-peer, which have helped realize the vision of federated information sharing. So we will compare the existing approaches based on the two key aspects: the goal of the policy system, and in our case we have to see if it meets the needs of the federated information sharing, and the design of the language used to construct the policy. Is the policy flexible and maintainable enough? All right. So in terms of policy goal, there have been policies designed for network security, database security, and even code security. But because of the fact that the collaboration architectures have only recently emerged, so these systems do not address the federated information sharing requirements that we have addressed before. On the other hand, the systems have policy languages which are feature-rich, and they are based on formal model, formal grammar specification, and XML DDDs. But such languages offer limited flexibility and maintainability. They are not based on any modular language components. They don't have any construction or maintenance methodology, and there is little support for deployment and integration. As you might imagine, in federated systems, it's much more important that the policy you should be able to deploy and integrate the policy because there are multiple systems that are interoperating. And so deployment and integration becomes a very important concern. Okay, so what needs to be done? We view that policy should be considered as a program. You need to design modular language components, and your policy should be configurable and maintainable using same methodologies as other software. And you should be able to deploy your policies in a uniform manner. The idea there is that just like you take a programming language like Java and C and develop a program to satisfy the requirements of your application, similarly we need to develop a policy language to construct policies for the security requirements of the end system. So we propose a development methodology based on the principles of software engineering, and we apply that to construction of policies. And keeping in mind the requirement for component-based, language being based on modular components, we use a component-based development approach. So our approach is called policy engineering. The motivation is a standardized methodology for design of policies using principles from security management and software engineering. And the benefit is that it provides uniform development and deployment of interoperable policies for access control in federated systems. Another benefit of our approach is that there are complementary efforts such as the Common Information Model by the Distributed Management Task Force. That model is designed for the network management policies. And our vision is that if policies are constructed using well-known methodologies, then policies for network management and this database access management can interoperate in a federated environment. And the work on my PhD thesis recently got accepted for transactional software engineering, which is a flagship journal of this community. And so this gives us some recognition for our work, which is good in a sense because we proposed a novel concept of interleaving software engineering principles for the design of security management policies. And we believe that there's a lot of motivation for this idea, and we see a lot of potential for this work in future. So, to summarize our contributions, we have identified and developed key language components that address the requirements that we have just discussed. To satisfy the requirements for attribute-based access control, scalability, and federation, we have developed attribute-based credentials. For autonomy and decentralized administration, we have developed declarative rules. And to satisfy the constraint requirement, we have developed constraint definitions. And our policy engineering methodology brings these components together in the design of our policy language and a UML-based meta model. So this was the introduction and the motivation behind the work. Are there any questions so far before we go into the detail of the framework itself? All right. Let's keep going. So the policy framework consists of a policy specification language, Our policy specification language is based on an extension of the role-based access control model, which is recognized for simplified administration. Our language is called XML-based Generalized Temporal Role-Based Access Control, and it extends RBAC for the extension necessary for access management in federated systems. So let me give you a very brief overview of RBAC. RBAC comprises of 5 main components: users, roles, permissions, and a user-to-role assignment relation and a permission-to-role assignment relation. The key idea being that permissions are assigned, instead of assigning permissions directly to users, permissions are assigned to roles. And the users obtain those permissions by acquiring the roles. Okay, so how do we represent the requirements in terms of the role-based access control model? We have designed a formal grammar called xGrammar, which follows the BNF syntax, but the key distinction is that the grammar is designed to allow translation into XML schemas. So one of our contributions is that we extend BNF syntax to allow compatibility with XML schema specification. What this means is that the terminal symbols in our grammar can have attributes, and the attributes have data types. So this is at the top level syntax of our grammar. As you can see, the start symbol is the policy definition, which reduces to a policy terminal symbol. The terminal symbol has an ID and a name attribute, and the type of which belongs to the XML schema specification, and therefore the XML schema serves as the type system of our language. There are 5 non-terminals within this policy terminal symbol, and they represent the 5 components of the role-based access control model, namely the user, role, permission, user-to-role assignment, and permission-to-role assignment. And we have a non-terminal for constraint definitions, which represents the extensions to the basic RBAC model that we have proposed. So we will go into the details of all these non-terminals because they represent the language components in our framework. To summarize the language, we have 3 language components: credentials for user, role, permission, assignment rules for user-to-role and permission-to-role assignments, and constraints, which include temporal and non-temporal constraints. All right, so before we go into the detail of the language components, I would like to give you a high-level overview of the framework. The user, role, and permission credentials are used to construct assignment rules, and the constraint components are then applied on those assignment rules. And therefore, using our methodology, the 3 different types of components come together to compose the overall policy specification. And this picture gives you the idea of how we emphasize modularity and flexibility in policy design. So we will now go into the detail of each of these components and take a look at the policy and the xGrammar. So this is the user credential. The convention that I've used here is that all non-terminals are represented in bold. And so a user credential includes the credential type. A credential type is used to associate a user with a particular category. To give you further motivation, consider a federated digital library example where multiple academic institutions come together to allow their users to share library resources across their online libraries. So consider that Purdue has a database of users, John 1, John 2, and its library has a resource called libresource level 2. And imagine other users from other institutions trying to access the level 2 resource from Purdue library. At this point, you have 2 concerns. Number 1, how is Purdue going to recognize the students from other universities if it does not know their identities? And as we said, if you replicate the identity database, if every school replicates the identity database from every other school, you will lead to the problem of rule explosion, where you will need to maintain one set of rules for every single student across the entire federation. So to minimize these problems, we propose the following strategy. Suppose it is known that Purdue allows students